today's topic is magneto-thermal coupling. After first a short introduction, we'll go as usual in the governing equations. In this case, this is the heat conduction equation. We'll extend it to moving media because this allows us for a very nice modeling procedure for induction heating processes. And of course, we need the eddy current problem. And then we'll discuss how these two PDEs are coupled and also review a few applications where the modeling strategy is actually applied. So let's go again, go into the physical principle of magneto-thermal coupling. So we know that the alternating magnetic field induces eddy currents in any conducting material. Without alternating fields, by Faraday's law, we have, of course, also no induced eddy currents. And these eddy currents dissipate power, which are just Joule losses due to the resistivity in the conductor. And these Joule losses are, of course, heat sources. So they serve as an input to solve for the temperature field. So we have some heat sources originating from the electric field that is induced via the magnetic field. And this temperature field in turn can, of course, impact the magnetic field by temperature-dependent material properties like the electric conductivity and the magnetic permeability, which can often be temperature-dependent. So these are the physical principles. Let's now look at some applications. So, of course, this is the term is induction heating. So we have some technical applications, which is surface hardening, for example, for gear wheels. Stress relieving, tempering, or annealing can be done by induction heating. We can do hardening. We can solder by induction heating. We can even weld by induction heating. There are induction furnaces. And of course, at home, we might have an induction cooking plate. So we'll now look at some special induction heating processes, in particular for continuously moving structures. So often the heated piece moves with a constant speed. In this case, we have a thin steel sheet here, and it's actually moving in the constant speed through the inductor. So it has a low temperature before the inductor, and here we induce heat by the eddy currents, and we want to have a target temperature after the inductor, for example, in the production machine where we have to heat up the steel sheet, which acts as a tool. And here, in particular, a steady temperature is of interest. Not really the heating process itself, but the steady state temperature that we will obtain when we have the process in the steady state. And in principle, for such setups, there are two main sources of how the inductor can be placed. First, we have the longitudinal flux heating. So here, the orange thing is the inductor with the alternating current. So the magnetic field is going like for the dotted lines here. And we have the magnetic flux in longitudinal direction of the steel sheet. Whereas in the transversal flux heating, we have an inductor either on both sides of the steel sheet or only on one. And the magnetic flux is transverse to the sheet plane. We'll look at continuously moving structures in induction heating in detail. If you want to look for more detail, you can look at the PhD thesis of Klaus Robert, where most of the things presented here are given in detail. So let's look at the governing equation. First off, let's look at the heat conduction problem. And we can derive the heat conduction equation, the heat PDE, by looking add the first law of thermodynamics, which is given here as the change of the inner energy, which we will obtain by heat transfer across the control volume and heat sources P within the control volume. So the change of inner energy, we can assume an incompressible medium and use the caloric law. So the total change of inner energy is given simply by integrating rho Cp and the temperature, the absolute temperature. Of course, we wanted the time derivative, so we have the time derivative of the temperature here. The second term in the equation was the total heat flux over the system boundary. And here we can again just write down the boundary integral over the closed boundary of the control volume. And we have to integrate, of course, the normal heat flux. So Q dot is the heat flux density vector, and N is the normal direction of the boundary. And then here we can use the divergence theorem to transfer the boundary integral into a volume integral by introducing the divergence. And finally, we can insert Fourier's law, which is valid in solid bodies, which we treat for induction heating processes. And finally, we have another term, the total dissipative power. So these are the Joule losses, and they are given as a heat source here. And of course, again, we have to integrate the Joule, the heat source density over the volume to get the total value. So if we insert all these terms, this yields the heat conduction equation if we just leave out the integrals again. So this is a well-known equation. However, now we haven't treated the moving structure yet. And this we can do by using Reynolds transport theorem. So we can switch to a version for a moving control volume and obtain this convective term here, where we have rho Cp and velocity vector in the gradient of the temperature field. So this is now our equation we need to solve, and we note that this is the classical convection diffusion equation. Okay, so the heat problem is settled, except for the boundary conditions, which of course are also important. Here we have the standard boundary conditions. We have essential Dirichlet boundary conditions where we prescribe the temperature, for example, for the start temperature of our steel sheet. We have Neumann boundary conditions. So this is the natural boundary conditions prescribing the heat flux either to a prescribed value or we describe the heat flux over the boundary being 0. We can include convective heat transfer by using a heat transfer coefficient where we have where we prescribe the heat flux vector as heat transfer coefficient alpha times the temperature difference between our domain and an ambient temperature. And of course, this coefficient alpha is depending, for example, on the flow conditions of the medium around our considered domain. And finally, there's the Robin boundary conditions. This can be, for example, used for contact between two domains with different thermal conductivities. Just also note that we have neglected any heat radiation, which could be just for free space radiation, also considered via a nonlinear boundary condition. Finally, we need some material parameters for the heat conduction equation. We've seen already the density in the equation. This is usually not temperature dependent. What is often temperature dependent is the thermal conduction, lambda, and the heat capacity, Cp. And here the temperature dependence can be significant. On the right-hand side, you can see a picture for a typical steel. The temperature, the difference in the material coefficients, if it's significant or not, depends also on the temperature range that you have in your problem. So if you have a small temperature range, it might not be significant. However, if you have a larger temperature range, the differences can be pronounced. And then the heat conduction problem becomes nonlinear. So how do we solve the heat conduction equation? We can derive, with the finite element of method, of course, we can derive the weak form in the standard procedure. We will obtain a new or non-standard term, so to say, which is the convective term that looks like this. And we can use standard Lagrangian nodal finite elements. The challenge when solving this is that the convective term may lead to instabilities. So especially for time-dependent problems, you have to adapt your time scheme to something sufficiently stable. Furthermore, it results in non-symmetric matrices. You can see this here already by the convective term. This is not a symmetric bilinear form, and therefore you have to store the full system matrix, and you can't exploit the symmetry that you usually encounter in the heat equation. Good. The next problem, a subproblem for induction heating, is the eddy current problem. And here we want to describe the magnetic field by the eddy current case of Maxwell's equations. So in the classical A formulation, I've written it down here, including the convective term in magnetics that takes a moving conducting material into account, since our steel sheet is actually moving. We've also taken into account the non-linear material magnetic relativity, which might also be not time dependent, but temperature dependent, of course. We know the impressed current density, and we also know the velocity. So if we now solve for the magnetic vector potential, we get as post-processing result the electric field in the conductor, which is given by the time derivative of the vector potential, and the corresponding eddy current density JE, which is simply the electric conductivity times the electric field. And then we can build the Joule losses by the inner product of current density and electric field. And so this is the input for our heat conduction problem is a post-processing result of the magnetic problem. Okay, so now we actually know all the ingredients to couple our two PDEs. So I've written it down here again, the two PDEs, the electromagnetic PDE, so the eddy current case, the heat equation, including the convective term, and the coupling is done via two mechanisms. First, the source term here on the right-hand side of the heat equation actually comes from the electromagnetic, from the magnetic subproblem as a post-processing result. And then we have another coupling mechanism, a back coupling, so to say, because the material parameters in the electromagnetic problem might depend on the temperature field. So here we have a few challenges when we want to solve this coupled problem. First off, we have to deal with the convective terms. We have usually severe timescale differences between the different PDEs, and we have various nonlinearities. So we have a nonlinear electromagnetic problem and a nonlinear heat problem, and furthermore, they are coupled via the given interactions. So let's now focus on the timescale differences. What is meant by that? First we focus on the coupling strategy. So let's focus on the coupling strategy first. First off, we have a weakly coupled system compared to strong couplings like mechanic, acoustic, or piezo coupling, where we actually solve for both fields simultaneously. In our case, we can solve for the magnetic problem first, compute our eddy current losses, and apply them as input to solve for the temperature field. Then, depending on if we have couplings via the material parameters, we have to iterate over this. So the Joule losses are the main part of the losses in the magnetic problems. In fact, there are also hysteresis and excess losses. However, for eddy current problems or for induction heating problems, so to say, they are typically neglected because we want to actually heat with the eddy current. So we aim for significant eddy currents. So this loss mechanism is the largest one. The interaction between the fields is through to temperature dependent material parameters. So here we can get a back coupling to the magnetic field. So therefore a iterative coupling will be necessary. So we would have to iterate these two problems in another loop. There are a few useful modeling assumptions. The convective term in the magnetic PDE can often be neglected. So the eddy currents usually are not really significant. The eddy currents induced by the motion of the structure are usually not significant in comparison to the alternating field. And we can exploit these large timescale differences between the PDEs. So let's look what is meant by these timescale differences. Typically in the magnetic problem, in the induction heating problem, we will have time ranges of microseconds. So we really have fast alternating currents with which we excite the inductor. So the magnetic field oscillates really fast in comparison to the time constant of the thermal field. So typically when you will switch on your inductor, you have, I don't know how many 100 periods of the magnetic field until the thermal field actually reacts and goes into a steady state temperature. So the time constant of the thermal field is much larger than the magnetic field. And if you want to couple this phenomenon strictly, so to say, you would have to stick to the small time constant. So for each time increment you do for your magnetic simulation, you have to solve the thermal problem, compute the new temperature, and then iterate until you have convergence between the two fields. However, often this is sufficient to actually solve for the steady state of the magnetic problem. So we look at the frequency domain, we have over one period, we solve the steady state of the magnetic problem. If this problem should be nonlinear, we can do the multi-harmonic solution of the magnetic problem. And then we apply a period average Joule loss as a heat source to the thermal problem. And we can compute the thermal problem either in the steady state, or we can compute it in a transient simulation to actually see the transient behavior of the heat problem. Okay, so let's have a look at the Joule losses, especially for multi-harmonic magnetics. So how can we get these period averaged Joule losses? So let's start off from the expression for the Joule losses. We said this is current density times electric field. These are our Joule losses. So if we plug in our multi-harmonic ansatz and use the expressions we've seen before, we have this double sum. And of course, we want to have a period averaging. So simply we'll integrate over the period tau and divide the result by the period. So then we have the period averaged Joule loss. And if we insert this lengthy double sum here, we can, the product of the two sums, we can write it as a double sum with different indices, and we can use a trick that we can do when we integrate over a complete period. Most of these terms will actually be zero. So only a sort of DC component remains. We can actually use another identity of the complex Fourier series, namely that the corresponding indices AK and A minus K are actually conjugate complex. So we can use this here and write this then as the absolute value of our harmonic amplitude. So thereby we get the period averaged Joule losses for multi-harmonic magnetic simulations. Of course, the harmonic solution with a single harmonic, so the standard steady state frequency domain solution is a special case of this expression with only a single harmonic. Okay, so this formulation is actually implemented in OpenCFS. We can do the nonlinear eddy current problem in the time domain. We can do the transient nonlinear heat conduction problem. We can couple these in an iterative coupling, taking into account temperature-dependent material properties. And we can also do harmonic balance FEM for the eddy current problem and couple this in a forward manner to the steady state heat conduction problem. So now let's look at some application examples. Here we have a thin steel sheet that is heated by an inductor. It's bent like this. In fact, this is only 1/2 of a symmetric model. Dimensions are given here and we'll excite this with a constant current density of 5 kiloampere oscillating at 5 kilohertz. We'll assume a nonlinear pH curve for the steel sheet, and we can exploit the symmetry. So we can again model half of the sketch shown before. Let's look at the computational mesh. Of course, we need to resolve the skin depth. This is approximately 0.7 millimeters in this case. So the element size in the steel sheet, you can see it here. We have about 10 elements over the thickness of the steel sheet. In the sheet direction, we can be a bit coarser, and in the air volume, we can be much coarser. And to nicely couple these two domains with different meshing requirements, we will actually use non-conforming grids to couple to the surrounding air. So let's look at some selected results when we now look at the time domain solution of the magnetic field in the steel sheet over one period. We have the transient reference solution as a dashed line here, and depending on the number of harmonics n, we see that more harmonics, of course, approximate our solution better. So a fairly high number of harmonics is actually needed to get a really good agreement here. If we look at the relevant quantity, however, being the Joule losses, the total Joule losses in the steel sheet, we see here a comparison for different number of harmonics, the absolute value of the Joule losses and the relative error with respect to the transient reference solution that we see already with actually only 3 harmonics, where the agreement of the signal itself is not that great. We only have 4% error with respect to the reference solution. And this can be reduced down quite a bit if we take into account more harmonics. However, with a single harmonic, we're about 12% off. So this is probably too large of an error to just use a linear model for the magnetic problem. So this was an example for induction heating of metal sheet. Regarding computation time as information, the multi-harmonic answer was about 7 times faster than the transient reference solution in this case. So that's quite an improvement, especially if you want to, for example, optimize an engineering design. Here there's a reference where you can find details on a similar application example. And another example here to show for more realistic induction heating process, in fact, we can take into account, of course, the end effects of such an inductor. Here we have the connections basically modeled in full. And we also know that, in fact, such an inductor needs to be water cooled. So there's water flowing through the inductor. So it's, in fact, a hollow cross section where eddy currents can develop. So this is important to consider, which is not possible with the formulation presented here. I've given you a reference afterwards where you can find out a bit of detail about this formulation for the eddy current problem. But just to highlight a few of the results. So here the steel sheet is moving again through the inductor with a constant speed. Beneath the inductor, it's moving in this direction U. And if we look at the temperature profile along the motion direction in the center of the sheet, we see we have an initial temperature before the inductor, and here we bring in the heat from the inductor, so the temperature rises. This is the second loop of the inductor, so these are these two locations where the current is flowing in one direction and in the other direction, and so we'll do the eddy currents basically imprinted in the steel sheet. So we have these two increases in temperature, and you can see that after the inductor we have a slight decrease in temperature simply by the loss due to the boundary conditions to the surroundings. What we see here is that when we take an increasing number of harmonics, our magnetic simulation gets more accurate, and we can better compute or more accurately compute the losses, and therefore we get a more accurate temperature after the field. In fact, in this case, you see the temperature difference is not that high, so a linear approximation is not that bad in this case. What is also important in eddy current problems is to find the optimal working point, so the good operation frequency of the inductor, and this is done by computing the efficiency either, which is defined by the Joule loss power over the active power in the electric system. And there you can see that for a certain frequency, in this case of a few hundred kilohertz, we have an optimal efficiency. I've given here a few references on further related topics. I've mentioned the non-conforming grids for edge elements. There's a newsletter on that, and if you're interested in how to take into account the eddy currents in the inductor. You need a modified formulation for the magnetic problem, and details can again be found in the paper given here. Here are the references again collected, and finally we have the magnetothermal coupling question.